All right, practice exam. So let's take a look at these things. We'll go through each question. Basic definitions of stuff. You should all know what an imine is. It's just an example. Nitrogen double bond to a carbon, bond to another carbon. At some point, that's all. That's all an imine is. Tertiary amine, just a nitrogen bond to three carbons. It doesn't. These are just three methyls. It could be anything you want it to be. Of course. Enamine, same deal. Nitrogen bonded to two other carbons. Singly bonded to three carbons, I guess you'd say. Adjacent, right next to a CC pi bond. That's an enamine. Other ones we talked about are aminium. We talked about primary, secondary amines. We talked about quaternary amines. So those things you should know. For the second one, the thing to remember for this is, essentially what's happening here is the iodine is losing bonds to oxygen and this alcohol is being oxidized. All right. So the first step is an SN2. All right, we kick out the OAC. So we kick out the OAC. Right. And then when the OAC comes out, again, to them to remember, OAC is this. AC is just this acetyl part. So OAC minus is oxygen with a negative charge. You do a deprotonation. The hard step here is this kind of weird 3 arrow where this iodine oxygen bond takes that H. You make the pi bond and the electrons go back to the iodine. Pretty tough one to know. But we talked about it, we've shown it to you, but maybe this is kind of question I would give you the steps or something like that. Wanted to challenge you in the practice test. All right, so for this one, I wanted you to draw the missing reagent and mechanism arrows for the reaction below. So I wanted you to recognize primary amine. If you look at the product, you see there's 3 things added that are all the same. So this is like essentially an amine being alkylated, or essentially doing a series of SN2s. You can't stop it at secondary or tertiary. It goes all the way to quaternary. So you needed to find something that had a good leaving group because, right, I talked about this. Amines are nucleophiles. Their bases are nucleophiles. Right, so the nitrogen reacts to that carbon. Does an SN2. I picked a bromine here. Doesn't have to be a bromine, but it has to be a good leaving group. So OH is not a good leaving group, right? So remember that. So Br here is just a leaving group, all right? It's making this carbon an electrophile, right? Making that carbon electrophile. The nitrogen's a nucleophile. SN2. Made Br minus. Br minus then deprotonates, right? Deprotonates, right? Back to a secondary amine. The secondary amine does another SN2, right? Because this is an excess. Br minus again does a deprotonation. Now we have a tertiary amine, and we still don't stop there. Does another SN2. So we've made 2 HBRs. And then this last step, we make a nitrogen plus, and I should have had these 2 things there to be able to do this problem as well. So for this one, professors make mistakes too. Folks hopefully can do the resonance. Make sure you're showing the right single-headed arrow. Make sure you're showing it to the bond, the other electron going to the atom, right? All those kind of things. You should get a secondary. You start with a secondary, and a primary. So there's no real difference between these. Primary would be the least stable, but I just didn't write the question very well. The idea would be to get to either I see which one's the most stable or the least stable. You can think about hyperconjugation in those kind of ways. So for this one, draw the mechanism for the reaction, give me the steps: protonation, PT, addition, PT, elimination, addition, deprotonation for PT. So the first step, even if you didn't have the steps, hopefully you see H+, you always protonate, right? And all these reactions, these aldehydes, the carbons of the carbonyl are the electrophiles. Protonation, solvents in excess, right? So that's going to be more likely to react because there's just a lot of it around. Oxygen lone pair adds in, right? Add in. We make a tetrahedral intermediate. We do a proton transfer. Makes this into a water, which is a good leaving group. Do an elimination, kick out the water. Have an oxygen from inside the same molecule. Instead of having another one of these react, we do it within the same molecule, that intra-molecular reaction. Oxygen adds in, kicks up. So that's an addition. Final step, proton transfer, deprotonation. Hydrogen falls off, you regenerate H+. Don't forget there's a hidden hydrogen here. I just kind of showed it throughout to keep track of things. Another here, give the mechanism. So I'm not giving the steps now, but hopefully you're kind of getting the beats down. First step, if you have H+, you better do protonation, proton transfer, making the oxygen of the carbonyls protonated. The amine adds in, proton transfer, make a tetrahedral intermediate. Do another proton transfer to make the OH a better leaving group, right? Because we don't want to kick out the thing we just added. Lone pairs come down, kick out the water, make the, right now it's like an iminium, but then after one proton transfer or deprotonation, right, because this is a catalyst, you get the imine, right? This is an imine. Now for the second step, you have an imine, and you're just going to go to a amine, secondary amine, right? 2 carbons. Now how does that happen? So I wrote it here, draw out the structure for sodium cyanoborohydride. But what I wanted you to recognize was Na+, right? And then boron has the minus charge, has 3 H's, and then the Cn is also bonded to the boron, but it's not adding in. Now how do I know it's not adding in? Because, right, there's a hidden hydrogen here, right? So I want you to recognize that. So this reacts like sodium borohydride, BH4. So even though the boron has a negative charge, the electron density is at the hydrogens or the carbon, but the hydrogen is what adds in, kicks it up, right? Tetrahedral intermediate, no good leaving groups. So go to step 2, protonation, we get the secondary amine. So number 7, mechanism for this. Essentially, this looks hard, but it's just making an imine, well, the one we just did. Protonation, nitrogen adds in, proton transfer, nitrogen made the water, nitrogen comes down, deprotonation, proton transfer, right? You regenerate the catalyst, you get to this. Essentially, it's called a hydrazine, but for you, it's just an imine, right? This is where it gets different. So this is where things kind of divulge a little bit, where all of a sudden now we're in OH minus, and you notice from here to here, the nitrogen's gone. That must become nitrogen gas. And there's 2 new H's here, right? Even though they're not drawn in, they certainly are there. And so the Wolff-Kishner is a way to turn a ketone, right, a ketone into an alkane. So what happens? OH minus, you're going to deprotonate. Right, this is hard because you're so used to adding in, but I want you to deprotonate. Do some elimination, right? That's actually really more like a resonance, actually. This should actually be called a resonance, but it's okay. Negative charge on the carbon, deprotonates the OH minus, deprotonates the water to give OH minus, which then takes another H off of there. So how do I know this is happening, right? Somebody should ask, like, how the heck? Just by noticing neither of these nitrogens have any H's. Right, so they have H's here, and now they don't have H's. And the 2 H's are here. So I need to take these H's off this nitrogen. All right, that's the kind of stuff you can write down on your test or exam and say, I know this needs to happen. And even if you goof up and don't get there, at least I can see how you're thinking and you can earn points for that, right? So we need to get the hydrogens off this nitrogen. So we'll keep doing that, protonate. It's almost like you're transferring the H's here to here. OH minus takes another one off, negative charge. The nitrogen kicks off, that's your elimination, make the N2 a minus on this carbon now, which is weird. We deprotonate and remake OH minus as a catalyst, right? That last step. Now, somebody did ask a good question, like, why would this ever happen? So the reason why this happens is because one of the byproducts is a gas. So it bubbles right out of the solution and you're done. So yeah, this happening, this carbon having a negative charge versus a nitrogen, is probably not very likely. But if it ever does happen and you start going down this path, there's no going back. So it's just almost like a matter of time for us to get there. So there's the Wolff-Kishner. So this one, given the steps, form this enamine, right? Notice it has to be on this side because there's no H's over here. First step, proton transfer. So you notice a ketone and a secondary amine is reacting here. If it's a primary amine, you can make imines, not enamines. Adds in protonation, it adds in proton transfer, whole deal again, eliminate water, right? You got this iminium, but because there's an H next door here on we call it the alpha carbon, the H can fall off, and you make the enamine because H plus is a catalyst. You know you're not done until you make the H plus catalyst. And there's your deprotonation, elimination type steps. So last one, mechanism and products. This is that diol reduction. Right, this is the one that turns esters into aldehydes, so you can maybe remember that. First thing you need to do is resonance. The O minus reacts with the aluminum. When that adds to aluminum, that gives the aluminum a negative charge, but it really makes the electron density in the hydrogen. And now since they're all in one molecule, that's that intramolecular reaction. Hydride adds in. We do the elimination, so that gets us the aldehyde. Then we have a plus charge of the aluminum and minus charge of the oxygen. They can come together to form this, or you keep them separate. It's fine. However you want to do it, it's okay, as long as you're balancing your charges and doing those things. So this one is really just an acid-base reaction, then an SN2. It looks harder than it is. People probably thought, oh no, he's going to make us do that whole rigmarole. But it's just K plus, potassium plus, OH minus, hydroxide, deprotonates. Then we just do an SN2, and you get to the product here. That's it. So some final radical chemistry mixed in. Again, just practicing, moving arrows, right? Be like move and break bonds, so I'll moving electrons. First step, right? You're just gonna break this bond. Single-headed arrows, one electron moves at a time. From here, how'd you know which one to take? Well, you saw that the bromine was gonna take an H, right? Hopefully. And so then it's like, what H could I take to make the most stable resonance, or the most stable intermediate, radical intermediate? So there's a pi bond, so I could either put it here or here. If it's here, it's a primary allylic radical, and if it's here, it's a tertiary allylic. And tertiary allylic's more stable. So you make that reacts with the bromine, makes a Br dot, and you add the bromine to that allylic position, right there. So this question is really kind of about understanding radical stability, and then also doing a good job with your arrows.